All right. Good morning, everyone. Welcome to Spring 2020. This is the class you're in, hopefully. Computing Systems Organization. So, what are we going to do this semester? My number one goal for you all this semester is for you to understand from the ground up what a computer is. So, starting with the most basic elementary components, all the way up through understanding how those components produce the abstractions to which we have become accustomed. My goal for you this semester is to understand every stage of that process. How does a digital circuit become a CPU? That'll be the first part we look at. Once we have a CPU, how do we program the thing? So we'll be doing some programming in machine language. Once you know about machine language, well, how does a high-level language become machine language? So we're going to write a compiler. How does a keystroke become a character on the screen? We're going to explore that too. So we're going to build a simple, primitive operating system, very basic, bare bones, nothing on the scale of what we study in the operating systems course as such, but enough to get a feel for how do the basic operations of hardware manifest as software. So by the end of this course, anytime you're programming, you should be able to construct a mental model of what the underlying physical machine is doing for every line of code you write in essentially any language. That's what we're going for this semester. That's the goal. To get there is going to require a lot of hard work. It's worthwhile. The payoff is going to be enormous, but be ready to put some serious time into this class. Every now and then when I teach this class, I get course evaluations saying, this class was a lot of work. And they're right. So I thought I'd mention it now, just to set the tone. Not only is it a lot of work, it's pretty cumulative. That is, if you don't quite get one project, the next one is going to be that much harder. So this is really a class where you've got to keep up in order to avoid getting behind. So just telling you, from the get-go, plan to put a lot of time into this class, but also expect to gain a lot from the time that you invest in this class. You're really going to get a lot out of it. You're really going to learn a lot, understand a lot, achieve a lot about just what a computer is. So that's that business. So that's me. Many of you, of course, have been in some of my previous classes. For those of you that have not, to get to my office is the last office on the left. So if you go to the MC Reynolds hallway up the stairs, take a left, last door on the left is my office. If you come up the elevator and turn right, again, it'll be the last door on the left, okay? I use BookMe for office hours, so you can just click on that and book an appointment with me. It'll automatically appear on my calendar, and I'll be expecting you. If my door happens to be open, you're always welcome to just come on in and chat, and I'll be happy to chat with you at least for a few minutes. I maintain a class web page, which is what the syllabus is on. You can get to this web page through the Moodle page for this class as well. So I'll be using Moodle in a couple of ways. It's going to have a reference to this syllabus page, which contains everything you need to know about the class. And then all of your assignment submissions will be through the Moodle page as well. Lecture time, let's see. All right. All but maybe one person figured that part out. Glad you made it. It's bright, it's early. I'll do my best to be chipper and worth being awake for, but definitely look forward to seeing you bright and early each time. Final exam period is going to be Wednesday, May 6th from 2 to 5 p.m. I always like to put this in the syllabus so that when you have to make travel arrangements, plane flights or whatever, you make sure they happen after that date. Required textbook is this right here. Unlike some of my other classes, for this course, I actually follow the book really, really closely. It's a good book. It's reasonably priced. I think it's like $30. And I think they may even have it online on their website as well. Like, you could just read it if you wanted. But it's pretty well written. I think it's worth getting. And like I said, we're going to be following it very, very closely. They have a web page for the textbook, which I think encapsulates the theme of the course. We'll be talking about that a little bit more today. You're going to need to go there to get all of their software that supports the book's projects. So there's quite a lot of it, digital circuit simulation, machine simulation, all kinds of stuff. So you're going to want to go there, download this big zip file, set it up on your machine, and be ready to use it. Okay, grading system. There are 1,000 points available this semester. To earn an A, you need to hit at least 900 of those points, and so forth. So, and then as I grade things, the scores will be on Moodle, and you can see what your accumulated point totals are and kind of estimate how you're doing from there. So this is where the points come from. So there are going to be, so the book has 12 chapters. Each chapter has a project. Now, I've taught this course a number of times, and what I've learned is the first 7 projects are easier than the last 5. So what I've done is early on, we hit these first 7 projects fairly quickly. Then the last 5, I've actually broken up into multiple parts. And so I've got lots of intermediate pieces for you all to complete to meet these various milestones here. 10 and 11, I'm going to do a little bit of an experiment this semester. I think it's going to go a little more smoothly to actually combine 10 and 11 into a single giant 4-part project. And so we'll see how that goes. Basically, Project 11 was the Achilles heel of a lot of students in prior semesters, and I think this is going to make it go more smoothly. We'll see. And then Project 12, I break up into 2 parts. So the projects in total are going to represent 60% of your grade. So you can earn up to 600 points from the projects. We're going to have a midterm worth 150 points and a final exam worth 250 points. So find a way to get to 900 from that, and you are all set. So a couple issues here. So as I mentioned, this consists of 12 projects that, when completed, result in a complete simulated computer. So we're going to start by building a CPU from logic gates. We'll build an assembler, a compiler, and so forth. Each project must be completed individually. So the idea here is you're going to get some programming practice and the like from these projects, but the real goal of each project is to understand where each abstraction comes from. It's a fundamentally individual process, so I expect you to complete them individually. So here are my parameters for collaboration. You may discuss any of the projects with any student in the class or anybody who's ever taken the class. That's fine. I'm cool with you having a conversation about it, strategizing about it, even going to a whiteboard, sketching out some ideas. Here's what I don't want you to do. I don't want you to read any solution to any project, whether from another student, found online, or from any other source. Complete solutions to all of the projects are easily found online. It's a popular book. Lots of people have posted their solutions. Here's the kicker. If I'm reading over your solution and on some intuitive level it just doesn't look like you, I'm going to take part or all of your solution and I'm going to go to Google. And if it turns out not to be you, I'm going to find it pretty quickly. How do I know that? Because I've done it before. And peoples have gotten D's and F's in the class over it. I think one semester, close to half the class plagiarized, and it was not pretty. Let's just say there were some retakes after that. So just don't do that, okay? Don't show your solution to any other student, whether this semester or in the future after you've completed the course. Don't give or receive help in debugging a project solution. Debugging help needs to come to me. No problem, book an appointment, send me email, whatever you need, and I'll be happy to help you. I know all of the projects really, really well. I'll be able to help you debug it. Okay. So just rely on me for that aspect, okay? And the issue is, if you ask another student to help you, it could kind of cross-contaminate with some of these other issues. And so really just to keep things fair and balanced and safe for everybody, for debugging help, just come to me, okay? All right, deadlines. So for every assignment, I've got it set up so that to get full credit, you submit it to Moodle by 11:55 p.m. on the specified date. I've got each assignment points broken down into parts. So whatever you've got done, I want you to submit, and you can get full credit. After that, I'll accept any patches you make anytime up to the start of the exam period for 70% of the credit. And I actually have, for every assignment, it's broken down in terms of, for getting this far, this is the number of points you get for on time, this is the number of points you get for late. You really want to get them done on time, both to maximize your points and to keep up with the material. But I'm pretty generous on this late policy because I don't want you to get discouraged or give up if you can't get it done on time, okay? So if you fall behind or whatever, please go ahead, catch up. You'll get the bulk of the credit and you won't get further behind in the class, okay? So cool. All right, so here's the schedule. Like I said, we're gonna hit the ground running. Project 1's due Friday. And I'll be going over what we're going to be doing for that very shortly. The first few projects with the digital circuits, we're going to be going through those extremely quickly. And this is in part because compared to material later in the class, they're not actually all that difficult. But that said, the scale, the pace of the class is going to be really fast right out the gate. So just giving you an overview then. We're going to go over Boolean logic today. We're going to go over Boolean arithmetic on Thursday. By a week from tomorrow, you'll have done basic Boolean circuits and arithmetic circuits. Then we're going to look at sequential logic, which is how we implement memory, RAM specifically. And by early February, we'll be hitting machine language. You'll have your CPU developed by mid-February. We'll have our midterm exam in kind of late February. So the midterm will basically cover all of the digital circuit stuff, machine language, and assembly language. Then the next part of the course kicks in where we study all the pieces of a compiler. So we'll first be developing what's called a stack machine, which is kind of an intermediate language between a high-level language and assembly language. So we'll be getting a lot of experience with the stack machine. Then we're actually going to pause and write programs in the high-level language that they provide in the book, which they call Jack, which is a thinly disguised version of Java, as it happens. And so you'll write some programs in it, get those wrapped up. We'll have spring break. Then after spring break is going to be hardcore working on the compiler. And that's going to be most of the rest of the semester. So we're going to do the major compiler projects in late March through mid-April. Late April, we'll hit the operating system pieces. Then we'll wrap up the course, and we'll have a final exam in May. That's the plan. Any questions on the syllabus? Well, let's get to work then, because we got a lot to do. All right. So to kick this off, so I stream my lectures to YouTube, And then I put links to them on the Moodle page for the class. So the idea is if you went over something in lecture and you kind of want to see it again or whatever, well, you can just do that. If you happen to miss a day of class, you can catch up on with the video as well. So it's meant to be a supplement for you all in case you need a little bit more than that. What I find in practice is about 80% of the class never watches them, but for the 20% that does, it's really helpful. So if it works for you, great. If not, no sweat. Okay, logic gates. So there is a notion that a computer, the joke goes, is all just ones and zeros at the bottom. And that's true. But we got to think for a moment about what that even means. So here's a way to think about what it means. At bottom, of course, any computer we use is just a circuit with a bunch of electricity in it. But what we do is we set up these circuits so that we can interpret those electrical signals in a way that's intuitive to us. At a high level, of course, you turn on a computer, some windows pop up, and it's all very intuitive, right? But deep down, that's just a bunch of electrical signals that then set off little colors to show up in particular ways that make sense to us, right? There's no deeper meaning there. A computer has no consciousness. There's no there. It's completely an automaton following basic material physical laws. So, at that lowest level, though, we need to think about how do we manage that electrical flow? How do we set it up in a way that has meaning? So here's a way to think about it. You can imagine in a circuit that at the end of the circuit, there's either lots of electrons or very few electrons. And you can imagine, and here we're just going to kind of trust the physicists. Okay. We kind of have to do that. Right? If there's a tiny amount of electricity, very few electrons, for convenience purposes, we just call it zero. And if there are a lot of electrons, for convenience purposes, we just call it one. That is, we attach a symbol to represent a collection of physical conditions. And we then engineer our circuits so that the end product of the circuit is either a tiny amount of electrons or a whole bunch. Not really falling in the middle. So, again, in trusting the physicists and the electrical engineers, the basic, most bare bones logic gate is known as a NAND gate. So what is a NAND gate? For any logic gate, we can describe its behavior using what's called a truth table. So let me show you the truth table for a NAND gate. So a NAND gate is going to have two inputs and one output. The inputs are just streams of electrons, and it can either be lots of electrons, a 1, or very few electrons, a 0. Okay? So let's draw ourselves a little truth table. So I'm going to have X and Y representing the input streams, okay? And then we'll have X NAND Y over here. So when we've got two inputs in a truth table, we can specify all possible combinations of the input values in the following way. So X can either be 1 or 0, alternating with a Y that is also a 1 or a 0. So you see how I did that? I did the X's, all the 1s together, all the 0s together. The Y, I made them alternate. And notice that for two inputs, each of which is either a 1 or a 0, there are 4 possible combinations. So I'm assuming you're all familiar with the idea of and. Somebody remind me what and is. Forget about the and part, the NAND. What's an and? Anybody? Yeah.
As long as both are true, then the output is true. But if only one of them is true, then the output is false.
Correct. So a NAND is like and, except it's not. Like literally, it's not. This is the truth table for NAND. If they're both ones, NAND is 0. Anything else, it's a 1. And you might be thinking, what a bizarre thing to start with. Let me tell you 2 reasons we're starting with this weird, bizarre logic gate, NAND. The first reason is this. NAND gates alone, networks of NAND gates suffice to create an arbitrary digital circuit. That's one thing. The other is, it turns out, for physics reasons, NAND gates are cheap to fabricate. It's very inexpensive to make these. So in other words, you can imagine Intel, say, or AMD, pick your favorite, has these manufacturing plants where they create billions of NAND gates on a chip. And then they just set up networks of wires connecting them. It turns out to be really cheap to do that. On an intuitive level, right, if there's just a single gate that can produce anything, economics of scale suggest, well, just use that. So a big part of Project One is going to be the process of each of you using NAND to build all of the most basic logic circuits, as a matter of fact. But I'm going to at least go over conceptually why that would work and give you a rough idea of how you're going to get there. Okay? So, why would this ever work? So, of course, you've seen and before, and you've seen or, and you've seen not. I trust this is review for everyone. So let's set up some truth tables for these, okay? So as we discussed earlier, and looks like this, or winds up looking like this. So somebody remind me what or is. What's the or of 2 bits going to be? Yeah, Andre.
As long as one value is true, the output is true.
Yep. And then there is not. Which takes whatever comes in and spits it right back out. Now, this combination of and, or, and not is what's called logically complete, by which we mean as long as you've got and, or, and not, you can build any digital circuit. But it's worth pondering for a bit why that's true. So let me see if I can convey some intuition about this. I'm just going to set up kind of an arbitrary truth table over here. Okay. And then, in a sense, what I'm getting at is it doesn't really matter what's over here. You can make up anything you want and put it over here on the right. But whatever you come up with, you can then emulate using and, or, and not. Now, how does that work? You can think of each row of the truth table as being expressible with and not. Here's what I mean. Let's imagine I'm demanding a 1 over here in the third row. I can express this as not x and y. Let's imagine I want a 1 in this row. I can express that as not x and not y. Now let's imagine I've got zeros up here. I just pretend they don't exist because they're zeros and they don't. But now here's the cool part. I can connect these with an or. And now I have mechanically synthesized a digital circuit from an arbitrary truth table using and, or, and not. This isn't, of course, like a full-blown mathematical proof or whatever, but it illustrates the concept of logical completeness of digital circuit operators, right? So, if these three guys, and, or, and not, suffice for logical completeness, if we can create and, or, and not just with NAND, then NAND suffices for logical completeness. Hint, you can, as you will figure out this week. Cool. Any questions so far? It's a pretty powerful idea. Literally any truth table you can construct with ands, ors, and nots. Literally any. As in, if you're ever in doubt about how to build one of our logic circuits over the next couple of weeks, if you're just totally lost, what you can always do is write out the truth table and read out of the truth table a circuit with ands, ors, and nots. That is, once you've figured out how to make them from NAND. So I'm going to go over with you all of the truth tables for the circuits, well, for most of the circuits, that you're going to be constructing in chapter 1 of the book. When I say most of, what I mean is this. You're going to start by making a lot of these little 1-bit circuits. Once you've got those, you're then going to make 16-bit versions of them. You'll forgive me if I don't write out the complete truth tables for those, I trust. Okay. But conceptually, they're very, very simple. If I ask you to build a 16-bit AND gate, all I want you to do is take 16 1-bit AND gates and put them all together on a circuit, right? Here's what I mean conceptually. Let's just imagine 4-bit, just for illustrative purposes, right? If I've got X is 4 input bits and Y is 4 input bits, I'm numbering them 0 through 3 to be computer sciencey about it. We'll see more serious reasons for that later on, but we'll just go with it for now. Well, if I want to AND these things, all I really need to do is take the corresponding single bits, AND them, and that yields the corresponding bit of the output. So if I want to build a 4-bit AND gate, I use 1-bit ANDs on the 0 bits from X and Y. That's going to be the 0 bit of my output. I'm going to do the same thing for the 1 bits of X and Y. That's going to be the 0 bit for my output. And then for the 2, and then for the 3. Like I said, this time we'll be doing like 16-bit ones. Might seem a little tedious, but that's okay, because that's what you got to do to build a computer. All right, so you're going to have and, or, and not, and that's colorful. What else? you're going to have a couple of circuits that you're probably less familiar with, but wind up being crucially important. The first of which is referred to as a multiplexer. Multiplexers are really cool circuits. In a way, I think you're going to find that they're like the if statement of circuitdom. Here's what I mean. Multiplexer is a 3-input circuit. Using the book's terminology here, we're going to call the inputs A, B, and cell. Cell, what is cell? Cell stands for selector. So the idea of a multiplexer is that you've got these A and B inputs, and the selector determines which of those inputs is the output of the circuit. Let me show you what I mean in terms of the truth table. So I'm going to do like 4 1s and 4 zeros for A. Why? Because I got 3 inputs now. Then I'll do 1 1 0 0, 1 1 0 0 there for B. And then my selector will be 1 0 1 0 1 0 1 0. So I'm actually going to go ahead and jump around a little bit to go from situations of minimum ambiguity to situations of maximum ambiguity. Here's what I mean. If they're all zeros, we know the output's a 0. Whatever the selector is doing, it doesn't have anything to work with. Okay? Likewise, if we've got 1s coming in on both A and B, it still doesn't matter what the selector is. It's going to be a 1. For that matter, if I've got 0s coming in on both A and B, even if my selector is 1, I know it's going to be a 0. Because the selector is just picking one of these. Okay? Now, the convention is if the select is 0, it's selecting A. And if the select is 1, it's selecting B. So now here's where it gets more interesting. So I'm going to go to the 0 rows, and then I'm just going to copy over the A bit. So here's a 0 select. My A is 0, so I get a 0. Here's a 0 select. My A is 1, so I'm going to get a 1. Okay, and I'm out of them. Now, if my select is a 1, it's going to be whatever B is. So here select is 1 and B is 1. Whoops. So that's a 1. Here select is 1 and B is 0. So I've got a 0. And that gives us, that's how we derive the truth table for the multiplexer. Again, the basic idea, the basic concept of the multiplexer is you've got 2 streams of electrons coming in. You're going to pick one. And whichever one you pick is your output stream. Like I said, you'll find it as you build more complex circuits that it's like the if statement for circuits. So multiplexers are tremendous fun to work with. I think you're really going to appreciate having them as a tool in your circuit toolbox. But if we have multiplexers, we should also have their inverse, by which I mean the demultiplexer. So what do we mean by a demultiplexer? Well, if a multiplexer picks which of 2 inputs is going to be an output, a demultiplexer picks which of 2 possible output streams the input gets routed to. So it's got a bit of a different feel. And it's going to be quite distinctive because it's the very first circuit we create that has more than one output bit. So what's the truth table going to look like for a demultiplexer? Well, first we have to talk about what our variables are. So we've got in and select. These are our inputs. They are exhaustive. Like so. And then we have our A output and our B output. So for each row, what we're going to do is determine both the A and the B output depending on the contents of the select bit. We follow the same convention that we use for multiplexers. That is, a 0 select says A gets the input and B gets nothing. A 1 select says B gets the input and A gets nothing. So let's look at the trivial cases first. If our input is a 0, we don't even have to worry about the select. Why? Because both A and B are getting nothing. Well, what if the input's a 1? Well, if my select is a 0, A gets a 1 and B gets a 0. If my select is a 1, A gets a 0 and B gets a 1. And that's a demultiplexer. Demultiplexers are also a powerful if kind of an idea in the world of digital circuits. Are also a very powerful idea. So that's what we got. Now, you might be wondering, what's all of this going to look like as a concrete assignment that we actually do? If you're not wondering that, you should be. So we're going to walk through that. We're going to be developing these circuits using what's called an HDL, which stands for a hardware description language. Hardware description language. It's going to look kind of like a programming language, but it's not. It's a circuit definition language. Again, it's going to look like a programming language, but it really isn't. So, how do we do all this? Funny you asked. Let's walk through it. So I'm going to jump back over to the class webpage, and I am going to scroll to the textbook webpage. So from NAND to Tetris is how they titled this webpage. Why? Because in this course, starting with NAND gates, you will develop a computer sufficiently powerful to play Tetris, if that's what you choose to do. Yeah. So, okay. So then what? Well, we click on the software link. Okay, good. And then we download the software suite. It's called nandtotetris.zip. Oh, I guess I need to hit that. Yeah, they've got it on Google Drive, I think. Yeah, the waiting is the hardest part. Okay, there we go. Of course, I got nandtotetris2.zip because maybe I've already downloaded this a couple times. That's okay. So I am going to show this in a folder. And I am going to, there we are. I'm going to extract all. And what I'm going to do is I'm going to just put it on my desktop. And I will show the extracted files when complete. Takes a moment. There's a lot in here. I like how in modern Windows it's got this little graph. So, oops. Oh, I just realized I already had unzipped onto my desktop before. Okay. So when you go into Nanda Tetris, you've got two folders, projects and tools. Let me show you the tools folder first. The tools folder contains a number of executable programs that are used to support this. There is an assembler, a CPU emulator, a hardware simulator, Jack compiler, a text comparer, and a VM emulator. For now, the one that we need is the hardware simulator. In order for these to run, you will need to have Java installed on your computer if it isn't already. I'm assuming most of you do because I'm guessing you've all taken data structures at this point. But yeah, all of these tools are written in Java. So what can you do from here? You go to File, Load Chip, and whoa, why is it looking there? All right, let's go up a level. You can go to Projects, Project 1, and there is an example here, the exclusive OR gate, which is provided for you. Okay. So I'm going to go ahead and open that up. And down here in the, okay, actually it's not provided for you. We're going to do it together in class because it's like in the book as an example. So we can see kind of the syntax for this language over here. And we can see input pins, output pins, internal pins, and so forth. And then later on, we can run a test script. So if I'm going to load a script, I load exclusiveor.tst, and then I can hit this run button, and it tries it out, and it tells me I have a comparison failure at line 3. Why is there a comparison failure? Because it doesn't work. And so this is how you can test your circuits and make sure that they work. In fact, it's how I will be testing your circuits and making sure that they work. So let's just make sure we're on the same page then. So right now we've got an exclusive OR gate that doesn't work. So we need to edit it. You can use really any editor that you want, any text editor that you want. I personally on Windows have grown kind of fond of Notepad++. That's actually where I edit my web pages and some other things. So what I'm going to do is I'm going to open this file within that. Desktop. My desktop's kind of busy. Maybe I need to clean it up a little bit. All right, so I'm going to go to Project 1, and I'm going to grab Zor.htl. So HDL, again, stands for Hardware Description Language. The book in Appendix A, I think, has a complete description of the language. But we'll see a lot of the salient features here as we build this particular circuit. So this has comments that should look familiar to you from Java. So you can actually put comments in these things. I'm not requiring that you do so for your submissions, but especially once you get to some of the later, more complicated circuits, I'll often break up sections of it with comments, like especially once you do the CPU. That one is pretty hardcore. So it's got end-of-line comments, block comments. Here's the main syntactic structure of the description language. Chip, and then the name of the chip. And that name should be the same as the name of the file without the .hdl. So it's kind of like declaring a Java class, right? Then curly brackets, break it apart. Then you specify on the inline what the inputs are. And these are all going to be given to you, the in and the out. And then parts is where you specify how it's supposed to be wired together. So before we go over how to wire it, let's go over conceptually what an exclusive OR gate consists of. And based on building that truth table, we'll think through what it looks like as a circuit. And we'll test it out and make sure that we understand how all the software works together. So So let's go back to the sketchy thing. There we go. So we're going to think about exclusive OR. Exclusive OR is a really useful and interesting logic gate. It, in some ways, maybe reflects a little more closely our linguistic idea of what OR is about. Exclusive OR says it's true if one of the inputs is true, but if both of them are true, forget it. Why? Because I am exclusive. Okay. So let's check it out. So we've got A, B, A, and then there's this traditional symbol for XOR, which is a circle with a plus sign in it. Okay. 1, 1, 0, 0, 1, 0, 1, 0. So we're going to think about what this looks like. Well, if A and B are both 1, I am exclusive. You are excluded. That's a 0. If A is 1 and B is 0, okay, we've got something to work with. That's a 1. 0, 1, that's going to be a 1. If they're both 0, there's nothing there. If two zeros put a 1 here, what logic gate would this be? Hint, we saw it earlier. It would be NAND, yeah. So I point that out just to say this is a handy way to kind of think about these things. Like once you really start to internalize these different binary logic gates, you should be able just in your head mentally to map them back and forth between the truth table, the name of the gate. Because in the end, whatever intuitions you have are trumped by its formal definition, which comes from the truth table. So part of just continuing to internalize this material is getting to that comfort point with these circuits where, given the circuit, you can just spit out the truth table just like that. Okay. That's something I'd like you all to aspire to. Okay. So looking at this, I'm now going to apply the methodology I described earlier for automatically figuring out how to build the circuit in terms of and, or, and not. So I ignore my 0 lines and I focus on my 1 lines. And I see, oh, if A is true and B is not true, that needs to be true. Or if A is not true and B is true. So here I've got an expression for exclusive OR expressed entirely in terms of and, or, and not. So now my task is to take this logical expression and create a digital circuit in this hardware description language. So that's what we're going to do. So just kind of memorize that. Well, I saw you all writing it down. Good, good, good. Okay. So I'm going to come back here. I'm going to think about how I'm going to build this. So I know that I need both kind of the unadulterated A's and B's, and I know I need them both to be negated as well. So I'm going to start by setting up the negated versions to have available as I assemble the circuit. So I'm going to use a NOT gate. And I'm going to say, and so actually let me look at NOT and figure out how I can use it. So I'm going to go to not.hdl. And I see that a NOT gate has a single input pin named in and a single output pin named out. So coming back over here to XOR, I can say that the in for NOT is going to be A. So what I've done here is I've said, I want there to be a wire from A to the input bit of this NOT gate. And now I need to say, where do I want the out to go? So what I do here is I literally make up a name. And that name that I make up becomes the name of what we call an internal pin in the circuit. And so in a fit of irrepressible creativity, I am going to call that pin not A. Go with intuitive names. Now I need to set up the inversion of my B input. So I'll say, so I create a second NOT gate. I say my input is B, and my output is not B. Again, I'm feeling uncreative. So glancing back at my circuit diagram, or my truth table, sorry, I've got my not A, I've got my not B, and I'm doing the ands first. So I'm going to go ahead and define my ands now. So coming back over here, let me open up and see what it makes available to me. So an and needs A, B, and then it'll produce the out. So coming back to my XOR, I'll say and A equals A. Now, this may look pretty confusing. So let's talk about what I just did here. My and has an input pin named A. My XOR has an input pin named A. The thing on the left-hand side of the equal sign is in the scope of the circuit that is receiving something. So when I say this A is bound to and, the thing on the right-hand side is in the scope of the circuit I'm defining. So that just equals A. Okay. So then I'm going to say B equals not B. So I'm saying the B input for my and is this not B internal pin that I've set up over here. And the out, I'm going to have to get creative again. I'm going to call it A not B. And now I'm going to do the same thing for my other and. So what's A going to be? Not A. What's B going to be? B. What's out going to be? B not A. That works. I mean, and is after all commutative. So I really was just going to call it not AB, but boy, did that look awkward. I actually prefer B not A. All right, so now I'm ready to look back at what I sketched out. So I've anded these and knotted them and all that. So now I just need to OR them. So I'm going to have an OR gate. I'm actually not going to look up its inputs and outputs because at this point I've got a pretty good guess. So A is going to be A not B. B is going to be B not A. And out is going to be out. In other words, the output pin of my OR gate is going to be wired to the output pin of my exclusive OR chip. So now, flush with excitement at my zest for discovery, I am going to reload my chip. And now down here in this window, you can't really see it back there, but like all my little chip B source code is over here. And now I'm going to run my test. Oh, wait a minute. Where's the test? Let me load my test. So load script, XOR.test. All right, there's my test. Now I'm going to run it. You know what? It didn't work. But there's a reason it didn't work. The reason is and not and or don't have any circuit definitions. Well, that's kind of deflating. So here's what I'm going to do. Because this is just for demonstration purposes. I am going to come over here. I'm going to go up a level, projects 01, and oh, not that, not, and or I think all of these guys need to be deleted. Oh, whoops. What do you mean it's still open? I closed that tab. All right, let's close the whole thing. It also got loaded into Hardware Simulator. All right, try again. All right, so they've been recycled. Now, what on earth did that achieve? Well, let me go back to Tools. I'm going to restart my Hardware Simulator. And now I am going to, you can actually just go directly to Load Script. And it said end of script, comparison ended successfully. Now, why is that? The Hardware Simulator is set up so it first tries to find every chip you refer to in your HDL file in the current directory. If it can't, it then just uses its built-in implementation to run it instead. So this could be something useful if you get frustrated at some point, right? So if you're kind of like, man, no matter how I try, I just can't make a not get out of an and. You could just move not to like some other directory somewhere, and then it'll be there for you. So it's an option. It's an option. So let me talk a little bit more about this hardware description language. Again, this is not a computer program. It sort of looks like one, it kind of feels like one, but it's not a computer program. It's a description of how a circuit is wired. Why something like this? In practice, in the hardware design world, nobody manually lays out circuits anymore. It's all done by computers at this point. Why is it all done by computers at this point? Why do you all think it's maybe all done by computers at this point? Any guesses, any thoughts? It's easier, right? So that's a valid, very valuable thing to say. It's easier, by which we mean the task in principle can be automated. So let's automate it and save ourselves some work. Okay? Good. What other benefits are conceivable from the fact that this could be automated? Yes?
Less involvement of human error.
Yeah, minimizes human error. Good. Any others? Let me talk about something that arises, right? What do you all think are the economic costs involved with different alternatives for laying out a circuit? Yes? So we've got some cost trade-offs, right? And those cost trade-offs have to do with physically how you've laid out the circuit. Let's think about what some of those cost trade-offs involve. Okay. So one way you can think about this is just total wire, right? You want to minimize the amount of wire that you're using. There are a couple of reasons for this. One, of course, is the more wire you have, the more material you need. There's another. The less wire you have, the less time it will take for an electron to travel through it. Yes?
That seems like a stupid question.
Go for it.
Literal wire?
Well, it's not like the wires that you use to connect components like this. It's more like a thin little strip of metal printed onto silicon.
Oh,
Yeah.
like in a computer.
Yeah. That's what I'm talking about with wire here. Just because it's the most useful term to describe what it is. So you're minimizing total wire. That minimizes both cost, but also is about maximizing throughput, right? So the less distance that an electron has to travel, the better, right? So then we also need to minimize chip space, right? So in other words, you've got a certain amount of silicon real estate. You want to pack as much into it as you can, right? And so again, computers are really helpful in doing that kind of physical layout, which leads to another issue, which is heat dissipation. So that's annoying, right? Unfortunately, nothing comes for free, and any physical motion by the second law of thermodynamics must produce waste heat. And that heat has to go somewhere. And that actually limits the degree to which we can minimize things. That is, you can't pack your circuits so closely together that they basically burn themselves up as they operate, right? You have to give them space to allow the heat to dissipate. I'm going to be doing a lot of nostalgia in this class. And the reason is, incredible though it is to say out loud, I began programming 39 years ago in 1981. Things have changed a little since then. But I'm going to make reference to this past life of mine every now and then. This is one of those moments. Back then, we didn't really need fans on our CPUs. They didn't generate the kind of waste heat that modern CPUs generate, where part of how we deal with the heat is to literally blow it away. I mean, there are running jokes about a real programmer can debug based on frying an egg on top of the CPU and based on the cooking pattern, understand what's going on. Anyway, yeah, modern machines generate a lot of heat. I mean, we've all felt it, right, when our phones overheat. Right, heat dissipation on a cell phone, man, that's a hard engineering problem because it's hard to build a fan into it. You know, desktop CPU, I mean, it's great, you know, the fan's in there and you know, when you're in the middle of a fairly good game and things are getting intense, the fan kind of spins up because there's a lot of heat to dissipate. So anyway, yeah, this is really hard stuff. And so some extremely clever people have come up with a lot of extremely clever algorithms that automate the layout to minimize these factors. It was fun when I was in graduate school, which is roughly the 1990s. I actually had a couple of friends whose dissertation research was in the area of improving the chip layout algorithms. And what happened by about 2003 or thereabouts was the algorithms had gotten so good that it basically became a solved research problem and they had to move on to other things. But I mean, they were doing incredibly clever stuff to really optimize these layouts. In a sense, neither here nor there, but I think there's some value in understanding the fact that if you were a professional designing a chip, you're not going to be doing anything at a lower level of abstraction than what we're looking at here. Make no mistake. Is it fun to just sort of wire this stuff by hand with a breadboard? Absolutely. Oh yeah, I love doing that stuff. But is that a practical solution for actually building a CPU in practice? Well, no. We specify the logic gates. We say this one's talking to this one. Then we let a computer figure out what it's going to look like on the chip. Okay, so let's take a few minutes and go over absolutely everything that you're going to be working on this assignment. So let's wait a minute. Oh, there we go. Back button. There we go. Yeah, cool. All right. So if I click on project 1, you can see the point scheme for this assignment. So like I said, for the full credit, you want to complete it by Friday. What I really recommend, of course, is that it's the first week. You've got so much time. If you don't have a class after this one, an excellent time to start on this is about 9:35. What do I mean by that? Come to a class on Thursday with questions. You know, if you're working on this, you get confused about something or whatever, if you start early, you've got more time for office hours, email, and to bring it up in class. You know, I'll be happy to kind of answer general questions in class, conceptual questions, okay? So, this is kind of the order in which I recommend doing them. So start with the not gate. Then not 16 is, it's literally going to be like copying and pasting 16 of these. Like normally copy and paste is like the worst thing ever. With circuits, it's sometimes difficult to avoid. You know, like when you're writing software, copy and paste is a sign of a design problem. And it means that we need to refactor the software. But for these, well, yeah, you're going to be doing some copying and pasting. So you'll have not 16, and 16, or 16. OR 8-way is a little bit funky. The idea of OR 8-way is it's going to have 8 input bits and 1 output bit. And if any of the 8 are 1s, the output should be a 1. So not super hard once OR is working, but it's a little weird, a little idiosyncratic. Make no mistake, every single one of these circuits is going to have a purpose. That is, every single one of these is something you're going to need to build a CPU. And in fact, some of them are set up specifically to make easier some of the tasks you're going to do in building your CPU. Then MUX is the multiplexer. MUX 16 is a 16-bit multiplexer. So what that's going to look like is there's still only 1 select bit, but the A and B inputs are each going to be 16 bits wide. And so much like AND 16 and OR 16, there's going to be some copy paste. Now, more subtle is MUX 4-way 16. MUX 4-way 16 goes from 1 select bit to 2 select bits. By 4-way, we mean there's going to be an A, a B, a C, and a D input. Now to build, once you start getting to some of these wackier circuits like MUX 4-way 16, something I really want to emphasize is use the highest level circuit you can to build it. Like, I don't want to open up your MUX 4-way 16.hdl and see a bunch of AND gates. You don't want to do that to yourself. Can it work in principle? Well, yes, you know, for reasons that we've stated, reasons we've gone over. Anything with a truth table, you can just build it out, right? But let me give you a little hint. A 4-way MUX just might have some other multiplexers in it as subcomponents. Those just might be useful. Similarly, there is the extremely cool MUX 8-way 16. That's going to have 3 select bits. It's going to be really useful to have 3 select bits going on down, by the way. Okay. It just might be the case that to do an 8-way, maybe a 4-way might help. Maybe even more than one, just saying, okay? Or in other words, yeah, in previous years, I've seen people do these the right way, and I've seen them work the wrong way, and the number of hours they must have put into the wrong way is difficult to imagine. So anyway, then you're going to do your demultiplexer, and you're going to have a 4-way version and an 8-way version. Note that with the demultiplexer, there's no 16. So with the demultiplexer, all we're going to do with it is only ever route 1 bit. We're not going to be moving massive numbers of bits around. The reason for that will get a little clearer later on, but it just turns out in practice, we don't need a 16-bit wide demultiplexer. They just don't prove to be all that useful for what we're doing here. Neat. And then, yeah, if you add it all up, the base score is 28. You get it done by Friday, you get 12, and then those bonus points are all distributed as you can see in the table. So, and in this case, it happens to be precisely 70%. So that's your first assignment. I think you're going to have a lot of fun with this once you get the hang of it. You definitely want to read the chapter and see what the authors have laid out in there. I think you're going to find that to be helpful. On Thursday, what we're going to do is start thinking about, once we've got all this stuff, how do we do math? And I think you're going to find this to be really interesting. The idea that we can take these basic and or ideas and turn it into circuits that actually do arithmetic. And something I think you're going to really enjoy about this is to see how, given how things work at the circuit level, how the profound ways that it winds up influencing the way that we perform arithmetic, even in a high-level language like Java. You know, I think we're going to be able to make some connections between that bit-level way of thinking about arithmetic and the way that it actually works, even in a high-level programming language. And even think a little bit from there about what would it mean to be even higher level than the way we do something like Java. In this class, we are not going to go beyond the integers as far as math. We're not going to do bit level floating point. It's interesting, make no mistake, but yeah, we just don't have enough semester. And yeah, floating point bit level is pretty hacky. For example, in floating point, there are 2 representations of 0. Yeah, it's funky. Yeah. If we have some extra time on Thursday, I think we might talk about some of those issues just for fun. But then what we're going to be going to from there is building what's called an ALU, an arithmetic logic unit. An ALU is the part of the CPU that does all the math. And once we've completed that ALU in chapter 2, we'll actually be, believe it or not, like about 1/3 of the way done with the CPU. ALU is a huge chunk of the CPU, actually. And thinking about how we can instruct the CPU to do lots of different operations is really key to getting useful work done with it. Cool. Any questions? Yeah, Andre.
I'm still confused on like on the Tetris part. Of
Yeah.
How the outputs are in and the inputs as well.
Okay, let's go back over it. So, over here.
Yeah.
Okay, so let's just walk back through it. I'm glad you asked. So, there are 2 different scopes we're working with. There's the scope of the chip you're working on and the scope of the chip that you're using. In the scope of the chip that you're working on is everything that's on the right-hand side of the equal sign. And the scope of the chip that you're using is everything on the left-hand side. So what we'll do is copy this and paste, let's paste it in here somewhere. Okay, I don't know where that font came from. I guess it's trying to look handwritten. Anyway. Okay, is that big enough to read in the back, the font? All right, cool. So yeah, let's imagine sketching this out, actually. So our XOR gate has an A input and a B input. So when I say not in equals A, out equals not A, it means I've got a physical NOT gate. This is in, that's out. My XOR A gets assigned to that in. So in equals A. And then the out becomes a pin. So this will be the pin, which is not A. Then I do the same thing down here. This NOT gates in equals B. That in equals B. Then the out goes to NOT B. So now I'm ready for some AND gates. So it has an A and a B and an A and a B. So my NOT A pin gets routed down here. My NOT B pin gets routed up here. Then I split my A, a second wire comes off of it. I split my B, another wire comes off of it there. And this is just a way of saying, when I say A equals A, what I mean is this A over here is the same electrical thing as this A over here. Okay? And then finally, I unite everything in an OR gate. So this pin is the A NOT B. This pin is the B NOT A. So then this A equals A NOT B. So A equals A NOT B. And then my B input equals B NOT A. And then its out becomes the out for my circuit. Does that make more sense, Andre? Cool. So it can be fun to draw these, but it also winds up looking like a big pile of spaghetti pretty quickly, which is one reason why, like, I think conceptually it's really cool to see that this is what the HDL is representing. Yeah, V.
Does order matter? So do you have to put A first, B first, output first, or it doesn't matter?
It doesn't really matter. Yeah. Yeah. So yeah, you can permute the orderings within here, largely with impunity. Good question. Any other questions? Right. Great. Well, I'm looking forward to working with you all this semester. We're hitting the ground running, and on Thursday we will talk about arithmetic. See you then.